The best way to describe the behavior of a random variable is to give its distribution. If somebody asks me what happens when you roll a six-sided die, I'd say you get 1, 2, 3, 4, 5, or 6, each with probability 1/6. If somebody restricts me to describing the distribution with one number, the one number that describes it as well as possible, well, it wouldn't be perfect because we've got these 6 different values. Let's say the expected value would be the best single number explanation of what the distribution is. So if somebody asks what happens when you roll a die, and I can only answer with one number, I'd say, well, you get about 3.5. 3.5 is the average roll if you roll a die. If somebody allows me to describe a distribution with two numbers, I think I would give the expected value, and then I would say how much the values of the random variable vary from the mean being the expected value. So are they always really close to that expected value, or do they tend to be kind of far from the expected value, or are they spread out on an interval? How much the values that the random variable can take vary from the expected value is called the variance. Let's look at a couple different distributions that have the same expected value as rolling a die. Let's look at a couple random variables, the sample space, the different values that they can take, the probabilities of each, and the expected value of each. So for random variable 1, I'm going to say we'll roll a die. So the sample space is 1, 2, 3, 4, 5, 6. The probabilities are 1/6 for each of those values. The expected value is 3.5. Now I'm going to define another random variable where the only values it can take are 1 and 6, with probability 1/2 each. So 1/2 times 1 plus 1/2 times 6 is 1/2 of 7, which is 3.5. So it has the same expected value as rolling a die. Now let's look at a random variable that can take values 2, 3, 4, and 5, with probability 1/4 each. So 1/4 of 2 plus 1/4 of 3 plus 1/4 of 4 plus 1/4 of 5 is just the average of 2, 3, 4, and 5. 7 and 7 is 14, so 14/4, which is the same as 7/2, which again is 3.5. Now let's look at a random variable x4, which can take values 3 and 5. The probability of 3 is 3/4. The probability of 5 is 1/4. So 3/4 of 3 plus 1/4 of 5 is 9/4 plus 5/4, which is 14/4, which again is 7/2, 3.5. Now let's look at a random variable that can take values 3 or 4. With probability 1/2 each. The expected value is 3/2 plus 4/2, which is 7/2, which is 3.5. And finally, let's look at a random variable which is not very random because the only value it can take is 3.5. And it takes 3.5 with probability 1, and obviously the expected value is 3.5. So these distributions all have the same expected value, but how far the numbers can get from the mean changes from one distribution to the other. So we want to describe how close to the mean is just another word for expected value, the different values can get, or tend to be. So, just to use the word variance, or a variation of it, how far how much do the values vary from the mean? So one idea is we could take the expected value of x minus expected value of x. How much do we expect the values we observe to differ from the expected value, from the mean? So if we try this for, let's say, x1, so we've got, try this for x1. So we'll have 1 minus 3.5 with probability 0.1 over 6, plus 2 minus 3.5 with probability 1/6, plus 3 minus 3.5 with probability 1/6, plus 4 minus 3.5 with probability 1/6, plus 5 minus 3.5 with probability 1/6, plus 6 minus 3.5 with probability 1/6. Now 1 minus 3.5 is negative 2.5. 6 minus 3.5 is positive 2.5. So if we add these together in this order, I think we'll see that this actually turns out to be 0. So this is negative 2.5 all over 6. And that's positive 2.5. 2 minus 3.5 is negative 1.5. And then 5 minus 3.5 is positive 1.5. 3 minus 3.5 is negative 0.5. 4 minus 3.5 is positive 0.5. 0, 0, 0. So this is 1/6 of 0, which is 0. So I think that doesn't quite measure what we want, because 0 doesn't describe how much these values vary from the mean of 3.5. In fact, we're going to get 0 for all of these distributions. In fact, we'd get 0 for any distribution if we tried to take the expected value of x minus expected value of x. And that's because okay, so this is not a good idea, bad idea. Let's let mu be whatever number the expected value of x is. So 3.5 in this case, but for some other random variable, it could be some other number. Then the expected value of x minus mu is, we know that if we take the expected value of a sum, it's just the sum of the expected values. So it's expected value of x minus expected value of mu, but mu is just a constant. So it's expected value of x minus mu, but mu equals expected value of x. So we're just getting expected value of x minus expected value of x, which of course is 0. That's because values to the left of the mean and values to the right of the mean are going to cancel each other out when we look at the differences between the value and the mean. Well, they'll cancel each other out unless we take the absolute value of the difference. I'll put up two better ideas. One is, let's take the expected value of the absolute value of the difference. Another one is, we could take the expected value of the square of the difference, because those are both going to end up being positive. I think that the first one makes more sense because what we're measuring is how far the values tend to be from the mean. And if we take x minus expected value of x squared, sure it's positive, but then we're measuring something that's a little bit weird. We're measuring this, what we expect the squared difference between values and the mean to be. So if we took every difference and then drew a square that had that as a side, we're taking the area of that square. So this is, I'd say, slightly weird. Because it really measures area rather than distance. But nevertheless, even though this second proposed formula is slightly weird, we're going to use the weird one. We're going to describe how much the values vary from the mean, we're going to take the expectation of the difference between x and expected value of x squared and see what that tends to be. So before we continue, let me see if I can convince you that there's a reason to do this, even though it's slightly weird. Okay, so let's leave the idea of variance alone and just want to show you a graph. So the reason that I'm showing you this graph is a justification for the definition of variance of x. How much the values vary from the mean expected value of x, and I'm proposing to define this as expected value of the squared difference between x and expected value of x. So let's suppose we flip a coin 10 times. X equals the number of heads. So I guess x is going to be one of the values 0, 1, 2, etc. up to 10. The probability that x equals any value k is, well, we have to choose k of those flips to be the heads, and then we've got 1/2 to the k for k heads, and 1/2 to the 10 minus k for 10 minus k tails. Basically, this multiplies out to 1/2 to the 10th. So we've got 10 choose k, 1/2 to the 10th. So let's graph the distribution. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are the different values that the variable can take. And turns out that these binomial coefficients go up to 250 if we look at 10 choose 5, or about that. So let me put 250. I probably should have moved this a little bit further to the right. Let me give myself a little bit more space. So these are probabilities. Each of these numbers should be understood to be divided by 2 to the 10th. So those give the probabilities. So the probability of getting 0 is, well, there's only one way to get it. It's 1 over 2 to the 10th. So we have a very low value there. And then if we look at 1, there's, I guess 10 choose 1 is 10 over 2 to the 10th, so maybe we're a little bit higher. And then the values we get are roughly 50 and 120. And 200. For 4, and 250 for 5. And then by symmetry, well, 10 choose k is the same as 10 choose 10 minus k. And then the power of 1/2 is 10 no matter what. We get the same numbers going back down again. Alright, so if we graph these probabilities, it turns out that there's a continuous curve that approximates, well, we can sort of connect the dots here. We wouldn't need to approximate for a number like 10 tosses, but imagine if we tossed 100 times, then we'd have lots and lots of different probabilities here, and it might be nice to have a smooth curve where we can just plug in 0, 1, 2, 3, 4, etc. To get the values we want. So this smooth curve approximation, maybe you recognize it, is sometimes called the bell curve or the normal curve. And the formula for the normal curve is y equals 1 over square root of 2 pi variance of x e to the negative 1/2 x minus expected value of x squared all over variance of x. So if we use the formula for variance that I just proposed, the second sort of weird one that has a square in it, we're going to get part of the formula for the normal curve. Actually, we'll get sort of two parts, because there's this fraction in front that's got variance inside the square root, and then there's the exponent that's got variance in the denominator too. So since this has variance of x, which again is expected difference between x and expected value of x squared, let's use this definition. For variance, because it'll be convenient if we ever have to use this normal curve. And not to give away the punchline of the course or anything, but this normal curve is very, very important. We'll see around the end of the course how important this curve is. So we certainly will use it. Alright, now that I've hopefully convinced you that there could be a good reason to use this slightly weird definition of variance, which is a distortion of what we want. We want expected difference, that is distance between a value and the mean. We're going to take square distance instead. So if we can accept that, let's look at some facts about variance. So we have another formula for variance, and that is we can write it as expected value of x squared minus expected value of x. Sometimes this is a little bit easier to compute than that. At the very least it has fewer parentheses in it, so that's a good thing. So the reason this is true, let's let mu be expected value of x, so it's just one symbol. Then the variance of x, which we define to be expected value of squared difference between x and expected value of x, is the expected value of x minus mu squared, which is the expected value of, let's see, x minus mu squared is x squared minus 2 mu x plus mu squared. And then expected value is linear, so we can write this as expected value of x squared minus 2 mu expected value of x plus mu squared. Now, expected value of x and mu are the same thing, so this is minus 2 mu squared. Plus mu squared gives us minus mu squared. Expected value of x squared minus mu squared. But that is, mu is expected value of x, so this is expected value of x squared minus expected value of x, the whole thing squared. Oops, I left out my square here. The expected value of the quantity x squared minus expected value of x, that whole quantity squared. So this is a formula we can use for variance sometimes. As a consequence, we know that variance is always positive because it's the expected value of a square of something, and the square is, we're going to get a bunch of different positive values here, or at least non-negative. So they can't be negative. So if we know that this is positive and this difference is positive, that means that the expected value of x squared is always greater than or equal to the expected value of x, the quantity, squared. So the expected value of x squared is greater than or equal to the expected value of x, that thing squared, for all random variables. And then another consequence is for any constant c, the variance of c is just 0. The reason is that the expected value of c squared minus expected value of c squared is just the expected value of a constant is just that constant. So it's c squared minus c squared, which is 0. And that makes sense because we're talking about how much different values vary from the mean. If the mean is c and the only value is c, then nothing varies. We always get just c. All right, now let's compute variance for the random variables x1 through x6 from the beginning. Alright, so I have to put up the definitions of these random variables again. So x1 was just rolling a die. So that could take any of the values 1 through 6. The probability of each is 1/6. Expected value of x is 3.5, which is 7/2. So expected value of x, the quantity squared, is 49/4. And I just erased the formula we want to use. Put it down here. Variance of x is the expected value of x squared minus expected value of x, the quantity squared. All right, so we've got this one. Now we need the expected value of x squared. Expected value of x squared is 1/6 of 1 plus 1/6 of 4, 2 squared plus 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. 1/6 times each of these, add them together, and we've got 10 and 20 is 30, and 55 and 25 is 55, 85 and 6 is 91. So 91/6. 96 is exactly 15, so this is a little bit bigger than 15. 15 and 1/6. Oh, that's the expected value of x squared. So actually, maybe we don't need that number right now, but so the expected value of x squared minus expected value of x, the quantity squared, is 91/6 minus 49/4. Let's see, that's 2 times 2 and 2 times 3. So if you multiply this by 2 and multiply that by 3, we can say over 12. So 182 minus 6 times 49 is like 6 times, sorry, we're multiplying this by 3. 3 times 49 is like 3 times 50, but minus 3. 3 times 50 is 150, so 147/12, which is, let's see, 82 minus 42 would be 40, but we're 5 bigger, so that's 35/12. And if we factor out, let's see, 5, we can't factor out anything. 5 times 7 and 3 times 4. This is almost 36, so that's a little bit less than 36/12, which is 3. maybe I'll start making a chart here again. The variance is 35/12. All right, and then we also did, let's see, the second thing was just 1 and 6. So our second random variable is just, has values 1 or 6, probability 1/2 of each. Expected value of x is 3.5, 7/2. So the expected value of x squared is going to be the same. I guess that's going to be the same for every random variable because I picked them all to have expected value of 3.5. So now let's recompute expected value of x squared. So it's 1 over 2 plus 36 over 2. So 37 over 2. 36 over 2 is 18, so it's 18.5. All right, maybe I'll write approximately 3 there so we just remember what that value is in comparison to the others. So this has a much higher variance. And I guess that makes sense because the only values we get are 1 and 6, which are relatively far from 3.5 in comparison to all of the numbers 1 through 6. I mean, these two numbers are far from 3.5, but the 2, 3, 4, and 5 are not so far from 3.5. So they contribute to values varying less from the mean than these values. These values vary from the mean. All right, and then the third random variable we had was the one that takes values 2, 3, 4, and 5. Each with probability 1/4. The expected value of x, so quantity squared is the same. Now let's look at expected value of x squared. So we've got 2 squared, 3 squared, 4 squared, and 5 squared all over 4. 4 and 16 is 20, 45, and 9 is 54. 54 over 4 is about what? 52 over 4 is 13, we know from decks of cards. So that's 13.5. So x3 takes values 2, 3, 4, 5. Probability of each is 1/4. The variance is 13.5. So there's a smaller variance here than here. That's because these values are closer to 3.5 than those values are to 3.5. All right, and then the fifth random variable. Oh, actually, I just did x4 wrong. Oh, that's not x4. x3 I did right. x4, we had two values here, 3 and 5. With different probabilities. Probability of 3 is 3/4. Probability of 5 is 1/4. The expected value of x squared is, let's see, 9 with probability 3/4. and 25 with probability 1/4. So that's 27 plus 25 over 4. 52 over 4, a number we know well, which is 13. So this value is a little bit smaller than that. X4 can be 3 or 5. Probability of 3 is 3/4. Probability of 5 is 1/4. The variance of x4 is 13. So we have one of the extreme values here and one of the interior values. So I guess without the two extreme values, the variance is a tiny bit smaller. All right, x5, what was that? x5 is just 3 and 4. The probability of each is 1/2. Another reason that this is smaller is that the probability of seeing 3 is greater than the probability of 5. So this is weighted a little bit more toward the interior values than toward the exterior values. Okay, now 3 and 4 are even closer to the mean than 3 and 5 is. At least the 4 is closer. So I would expect the variance to be a little bit smaller for x5. All right, let's compute expected value of x squared. So we've got 9 halves plus 16 halves. 9 with probability 1/2, 16 with probability 1/2. So that's 25 over 2, which is 12 and a half. Yep, sure enough, the variance is smaller. Alright, and then the last random variable, x6, which takes value 3.5 only. The probability of 3.5 is 1. Well, we know that the variance of a constant is 0. And this value is looking suspicious to me. 3 I think is too low, because there certainly should be greater variance here than with the 3/4. So let me check my work and see if I did something wrong. Alright, the problem's not there. The problem is in every one of these I forgot to subtract. I was just writing down expected value of x squared there instead of variance. So I really need to subtract. So we have 18.5 minus 49/4. So 18.5 is, let's see, 36 over 2 is 18. 37 over 2 is 18.5. 37 over 2 minus 49/4. Let's put this over 4. 37 times 2 is 76 fourths minus 49/4. 76 minus 50 is 26. 76 minus 49 is 27. So it's 27/4. 27/4 is just short of 28/4, which is 7. So it's a little bit less than 7. All right, now let's look at 13.5 minus 49/4. 13.5 minus 49/4. So 13 is 26 over 2. 13.5 is 27 over 2. So 27 over 2 minus 49/4 is 27 times 2 is 54. 54 fourths minus 49 fourths is 5 fourths. So 1.25. Okay, so this makes sense. This should be less than the variance of the first, because here we've got values 1, 2, 3, 4, 5, 6, and here just the interior ones, 2 through 5. So if we cut out those two extreme values, which are far from the mean, we'd expect the variance to go down. It did indeed go down. All right, now we've got 13 minus 49 fifths. So 13 minus 49 fifths is 26 over 2 minus, 49 fourths. 26 times 2 is 52. So 26 halves is 52 fourths. 52 minus 49 is 3 fourths. So we've got 0.75. And it makes sense that the variance went down because we're weighting interior number 3 greater than the exterior number 5 here. All right. X5. Let's see, the expected value of x squared is, I just erased it, 12.5. So 12.5 minus 49 fourths is 12 is half of 24, so we've got 25 halves minus 49 fourths, which is 50 fourths minus 49 fourths, which is 1/4. So 0.25, and then the variance of the constant, of course, is just 0. So we can see that when the values are very close to the mean, we've got a small variance. And then as the possible values get further and further from the mean, the variance increases and increases. All right, now let's look at a fact about variance of linear combinations. So if a and b are constants and x is a random variable, then the variance of ax plus b, variance is not linear, is a squared variance of x, and the b just goes away. The reason, well, let's let mu be the expected value of x. Then the variance of ax plus b equals, I'm going to use the original definition of variance here. So the expected value of ax plus b minus the expected value of ax plus b, that difference squared, which is the expected value of ax plus b minus expected value of ax plus b is a expected value of x plus expected value of b. It's just b. So this difference squared, which is the expected value of, let's see, ax minus a expected value of x plus b minus b, so no b's, that whole thing squared, factor x out of the square here, and I get expected value of a squared x minus expected value of x squared. Then the a squared can come out of the expectation because it's linear. Like a squared expected value of x minus expected value of x squared, and that's just the definition of variance. A squared times the variance. So the fact that adding a b here doesn't do anything maybe isn't surprising, because we're just shifting all the values of the random variable x by a constant, and that doesn't make things move further from the mean or closer to the mean. It just moves everything slightly up or slightly down, including the mean. So the values, the distance to the mean is going to be the same. And then, so if we have variance of a constant times a random variable, we can pull out the constant, but it becomes a square on the outside. And that's roughly because when we take the variance, we're taking the expected value of the square of something. So the fact that we're doing this weird squaring inside the expected value in our definition of variance is what makes constants come out to the outside with a square instead of just coming out exactly the way they are. Now for two random variables, the variance of x plus y is a bit more complicated. And we won't worry about that now. We'll do that later in the course. So that's enough for today. The end.